Okay, welcome everybody. We are going to try to code monodromy solving on the fly. So, sharing my screen now. All I have done is opened Julia. So let's make sure we can just see monodromy solving it all. Okay. Da-da-da. So sometimes whenever I code something, I do an example first because that really guides the actual functions. And you probably know by now that I'm doing this example. Everything's really baked into the quadratic equations. Yeah, you understand that. You understand most of what's going on here. Yay. U. How about 1, 0, -1? I like that one. That one's easy to solve, but not so easy that I know all the solutions. Rather, I only know the solution 1.
What was a system of like one equation?
Number of equations is 1. 1 variable, 3 parameters. Here are the equations. Okay. Now, let's choose a loop. So I want to choose a loop in the parameter space. What does that mean? Well, the first element is some point u. Second element, let's do like 1, 0 imaginary. Third element will be 1, 0, 1. Next one will be 1, 0 negative imaginary. And then this essentially is defining a quadrilateral where I go from a straight line from u to 1, 0, I to 1, 0, 1 to 1, 0, negative I. And I promise that this represents a non-trivial element of the fundamental group. I'm going around the discriminant, in other words.
Oh, yeah.
Sorry, going around the exceptional set. Okay, so actually, you know what? Let's stick u at the end also so we remember to go back.
Mhm.
Okay. The current solutions is S. Current parameters is u. Okay. And for L in loop. Yeah, let's say for P in loop to remind us that this is a parameter. Well, what do I want to do? I want to solve this parameterized polynomial system with start solutions, current solutions, start parameters, current parameters, and target parameters. Yeah, P. I will call that new souls. And of course, we want the solutions in coordinates here. So I throw solutions around it. Then I can set the current souls to be new souls. Current parameters to be P. I print. Okay, so this should do it. Target parameter is not fine. Did I spell it? One second. Let's see what I actually wrote. Yeah, there we go. Thanks, Julia. Saved me from making a mistake. So you see the issue is I didn't put an equal sign, I put a comma. Boink. Okay, and of course we ran home until big continuation for the first time today, and so it takes a while to compile. So we just wait here, we chat, we fill space, and we hope nobody gets too bored or leaves the class. Any questions about what's being written here? Raise your hand if you believe it's gonna work.
So I think here's a stupid question. Anyway. Here we go.
Hey. We have current solutions. So our solution is 1, and it happens at parameter 1, 0, -1. And then we have this solution, which is the 7th, 8th root of unity, I believe. And that is over 1. So it's x squared plus I equals 0. Right, so I is a 4th root of unity, so x squared plus I has 8th roots of unity. Yes. Solutions. Okay, cool. Yeah, and at the end, we went from 1 plus 0 times the imaginary number to -1 plus 0 times the imaginary number. Hooray! We need a polynomial system. We need the current solutions. We need this loop information. And that should be enough, right? Because now I can say 4p in loop. So yeah, we need okay, current params should be the first element of the loop. Okay, this is trusting the user, by the way. And then 4p in loop. New souls. Why not skip a step? We'll do current souls equals solutions solve. F current souls. Start parameters equals current params. Target is P. Oop. That's the solve. That's the solutions. Enter. We don't need to print anything. We can just return. Okay. So we got our loop. So I can do track souls around loop now of F. I think I called it S, maybe S1. Yeah, it's S. And loop. Awesome, something went wrong. Okay, when things go wrong, what do? We put those print statements back. Oh, I know what happens. I didn't reset what the current parameters were. Yay, good. Now we have an easy way to start tracking things around loops, okay? Let's do n equals 3. So this is going to be a random loop based at u with 3 vertices, okay? For I, yeah, so what do I want to do? I in 1 to n minus 1, because if we have 3 vertices, we need 2 more, for example. Push into the polygon, rand n complex f64, length of u. And then push into the polygon u.
I'm forgetting, what is length of u has to do here again?
Okay, so what do I want? Okay, so here's a u, it's my base point that I'm computing monodromy over. And I want to choose like 2 other points randomly and make the triangle from u and back. Okay, well, to choose those other 2 points, I need to choose parameters. How do I choose parameters? Well, I just need to choose 3 random complex numbers.
Which is the
3 random complex numbers, which is the length of u. So, 1,000 loops, random loop u for I n 1, 2. Ah, ha, ha, ha. No. Okay. Oh, it doesn't like that u is integer. U equals vector of complex F64 is of u. Okay, I just changed the data type of u. That was the issue. Boom, 1,000 loops. Whoops. Such a ridiculous sound. Okay, monodromy answers. Okay, let's see it. Okay. Wow, great. So I am tracking this one point around 1,000 different triangular loops. Sometimes I get one as my solution, which means the permutation was the identity permutation. Sometimes I get -1. Okay. The monodromy assumptions say those should happen with the same likelihood. Should be 50-50. Any guesses? Yeah. I think that the trivial permutation probably happens around 70% of the time. Let's check. So we want to filter these answers. Okay. Okay, so we get some solution set S. And we want to only take the ones where whatever function I'm about to write down is true. So let's say the real part of the first element is less than 0. Hey. So I get -1 about 37% of the time. Which means I get the non-trivial element of S2 37% of the time. Not too far off from my 70% guess. I just want to do a small explanation of why I thought this was the case. And just to build intuition here, our parameter space looks like this. Okay, I'm assuming A equals 1. Okay. The point I care about is this, u, 1, -1. Okay. And I'm choosing random things, so I'm kind of thinking that I'm looking at loops here. And I kind of feel like with about a 70% chance I'm hanging out in here. Albeit this is just a real picture, so it's not actually a legitimate argument. Tracks your intuition a little bit. Okay. If I chose something really, really close to the discriminant, I think I would see a lot more non-trivial permutations.
If you choose something exactly on the determinant, but no, that's not how it is.
No go there. Everything's nice. All right, soup it up. Y'all ready? Let's get a more complicated polynomial system. Ooh, let's do the polynomial system you should write down for coding part 1. So we will need a 1 to 4, I think, and B. I'm gonna get the support wrong, but so A1 times x plus A2 times y plus A3 times x squared times y plus A4 times x times y squared. That's our first one. B1 times x plus B2 times x squared plus B3 times x squared times y plus B4 times x times y plus B5 times y squared. Variables are x and y, so it will give me an error because I haven't defined y. Parameters equal a, the concatenation of a and b. Oh, I guess I told it what y was. Awesome. Okay. Ooh, uh-oh, I don't have a start solution. Any ideas how to get one? Oh, look, you're gonna, like, if you choose nice enough coefficients so that I can predict one of these solutions, they might be nice enough, they might be so specific that I'm on the exceptional locus. So I don't want to do that. So instead of fixing coefficients and finding a single solution, I will fix a solution and then cook up a random system that has to have that as a solution. Because I don't care really what polynomial system I'm over to start with. So let's say, yeah, let's just say x is 1 and y is 1, right? Then my parameters, well, I need the sum of the a's to be 1 and I need the sum of the b's to be 1, right? So random float 64, random float 64. By the way, observe that I'm just solving a linear system of equations. Okay. I agree. Now, if I pick a fourth one, they won't add up to won't add up to 1. So I synthetically add something so that they add up to 1. Good. Okay, for I in 1 to 4, push P, and then complex F64. Okay. And then push into P, what do I want? I want the sum of the 5th, 6th, and 7th elements, is that right? 5th, 6th, 7th, 8th. One less than that. Oh, P. Okay, so now I have 9 coefficients. Good, I have 9 parameters. Great. Oh, but I know a solution. So P equals start, U equals P. Okay, so that's my unit. Okay. S equals, make sure it thinks it's the right type. Okay. Good. So now we had this random loop function, didn't we? Can I get one? Random loop of U. Okay. Loop equals random loop of U. F S loop. See if it works at all. Nope. Let's check that we actually put this up correctly. Ah, we didn't get it right. They both add up. Wait, all of them add up to 1. Ah, I needed them all to add up to 0. Dang, sorry, everybody. If I evaluate these polynomials at 1, 1, I needed all the coefficients to add up to 0. Whoops. Okay. Okay. U is P now. Track solutions around the loop. Okay. Ah, I need the correct loop. Ta-da! It's a solution we didn't know before. Okay. Okay. My monodromy solve. F, S, and D. And U. While, yeah. Okay, so now I'm going to track solutions around, and I am going to get something new. And here is a crux of what's going on. How do I check if it's actually new? They're floating point numbers, you know. You got to check if two floating point numbers are the same. Okay, so best thing I'm going to do here is if the norm, so for S and S, so for everything that we already know, let's say possibly new is true. If the norm of S minus our new solution smaller than some tolerance, possibly new, it's false now. We're going to do that for all of them. So the only way you get out of here and have possibly new still be true is if the norm of the difference of the solution I just computed and everything I found is small. So if it's new, I do that. Which reminds me that this is not S, it's solution bucket. Okay. And let's go ahead and print something that we're really excited about. Yay, a new solution. There are now yay. Okay. Any questions so far? Eight. Okay. Hi.
Hi, Data. I don't think you're sharing the screen, are you?
Are you serious?
Yeah.
Yeah, you just have to change.
No, I'm recording. I'm just not sharing the screen.
Okay. Thank you.
I'm so sorry. That means this whole time I was not sharing my screen. Is that correct?
For a little while, you were showing it initially, but stopped at some point.
Oh, it stopped at some point. Do you remember where?
Uh, Not exactly sure. It's a little while back.
Okay. Okay, my apologies. But this will be posted. This Raw Julia session will be posted on the course webpage. So my apologies for it blinking out for a moment. Hopefully it wasn't too long.
Yeah, I think it's fine. Not too much.
Okay. Welcome back. This is the function we just wrote. It's called my monodromy solve because monodromy solve is already a function in homotopy continuation. So we can't name it the same thing. It takes in a parametrized polynomial system, a set of solutions that we do know, i.e. a single start solution, over some parameter u, and some d, which is a count of the number of solutions we expect. That'll be our stopping criterion. So as soon as we found that many solutions, we get to stop. And we assign our solution bucket to be the inputted solutions, and as long as that has fewer than d points in it, we're going to track our solutions around some loop. Which loop? A random loop based at u. And sorry, I see an error, so this should be the first element. Okay, we're gonna get a new solution. That may or may not be something we've already found, so possibly new is true. And then to check if it's something we've already found, we go through everything we have found, we compare it to the new one that we just computed, and if the new one we just computed and something we've already found are really, really close, so the norm of their difference is super small, then possibly new becomes false. After doing that whole loop, the only way you get out of it with possibly new being true is if it is indeed numerically distinct from the ones we found. If that's the case, we push it into the solution bucket and we celebrate. Otherwise, we grieve. And then I guess we should probably give an output too. Okay, we have a U, we have an S, and we have a D. I'm a little scared. Okay, track, loop. Let's just make sure this works. F S1, random loop, U. Okay, so that step works. Okay, so what do? We put more print statements in, yeah? Sorry, which means we kill the end. Okay, we're able to check whether or not it looks like something, so that's good.
Must be the norm of estimates.
Yeah, well, let's put a print statement after this to check if that's the case. I think it might be the type of output of track solutions over, but let's try that. Oh, it is upset at that. Ah, thank you. It takes a village. Indeed, it didn't want to take this norm. I see what happened. This is giving me a list. I want the first one. I'm only tracking one thing. Yeah, cool. Hip hip hooray. All right. So, hey, I found a solution. Checking if it looks like that. New, false. Brownie face. We already knew about that one. Hey, we found this. Checking if it looks like the one we know. True. It's new. Yay, a new solution. There are now 2. There are now 3. There are now 4. And as soon as we find like the 5th one, we have to check whether or not that new one is similar to all the 4 that we've seen, right? So in some sense, this is a quadratic complexity thing. So yeah, we have to do D steps where each step is, D steps where the ith step is finding solution I, and then at the ith step, we have to do something I minus 1 times. So it's like an I times I minus 1 as I goes from 1 to D. Okay. But hey, we get it, and we get the solutions. Let's just solve it explicitly. Compiling, it's compiling. Found 9. And the difference between that 9 and that 8 is part of your homework. One of these things is not like the others. Okay. And I think I'll end the recording at that. Many apologies for the screen sharing dying. But I hope it was okay. And now we have some base code for computing solutions using monodromy. And it really is, think about it, it's fundamentally different than start solution, target solution business, right? For a start system, target system. Okay, thanks a lot.